Machines. Here are your priming questions. Simple machines. You've probably learned from childhood that we have 6 primary simple machines: the wheel and axle, the lever, the pulley, the wedge, the inclined plane, and the screw. What you probably haven't realized is that these 6 simple machines are integrated into many parts of our lives, and they're seamless, meaning we don't really see that they are simple machines or that we are using simple machines, or something that we have is based off of or built through the use of a simple machine. So as a quick example, and these are just 1 or 2 examples, the wheel and axle, your doorknob, or every doorknob is based off of the wheel and axle. In order for you to move the bolt that is inside of the door, you have to turn the doorknob, which gives you a mechanical advantage to move that bolt. The lever, you can think of your seesaw at school when you were a little kid. If we have pliers, we have a specific type of lever. And also the way your bones move with the muscles, and in this case in particular is your arm. The muscle is attached close to the elbow, but it moves the rest of your arm. It's a lever. The way many parts of our bodies work is through the use of a lever. We also have a pulley. Pulleys are integrated into many different things. Here I'm showing you a simple crane that we might use to move our building and to move things that are very heavy. Pulleys can also be used to change the direction of forces, as well as to change the speed of rotation of certain devices. These are used in your cars for the timing belts. They're also used for the serpentine belts, for your alternator and things like that. These can also be applied to gear systems with chains, so a timing chain. And even deeper than that, the way our transmission works is very similar to the way a pulley works. For the wedge, wedges are used in a lot of different things. If you've ever split wood, you might have used a splitting maul or an axe. These are both different types of wedges. The inclined plane, if you've ever moved a heavy appliance, or if you've moved houses, you most likely have used ramps to load the truck. And without the ramp, things become very difficult. And for screws, we use these as simple fasteners to put things together or assemble things together. But also, there's an Archimedes screw that was used to move water up a certain distance. So there are many different applications, and some of these are actually combined together to increase the mechanical advantage. So that brings us to the AMA. The AMA is the actual mechanical advantage. You can think of this as a ratio of the forces. So it's going to be the FR over FE, where FR is the resistance force, which in many cases will be the weight of the object that we're trying to move. And the FE is the effort force. This is the applied force. Another way that I think about it is the FE, or anything with an AE, is the input. It's what you are putting into the system. Whereas the FR, or any of these that have Rs, is the resistance. And this is the output of the machine, or what the system is doing at the end. The AMA is the actual mechanical advantage, and this takes into account things like friction and air resistance and other non-conservative forces. The IMA, on the other hand, is the ideal mechanical advantage, and this is if we had a perfect system where there's no friction, no air resistance, only conservative forces acting, then this is the mechanical advantage that we would experience. This is calculated through the ratio of the distances. So it's the DE over DR. So it's the input distance divided by the output distance, if that makes sense. So however far you have to apply your force divided by however far that resistance, whatever you're trying to move, the force for that had to move. So if we were to think about an inclined plane, and let's go ahead and just draw an inclined plane. We'll draw it like this. If we're looking for the IMA of the inclined plane, we have to think about the distances and the forces. So in this case, if we were to have this inclined plane, we would be applying a force up the incline. And that's also the displacement that we would be going. Whereas for the object, the weight of the object would be going straight down. And so when we are looking for our dE, this would be our effort distance. But when we're looking for our dr, this would be the vertical, this would be our dr. You have to look at the forces and the displacement in relation to those forces. They need to be in the same direction. If we're looking at a lever, so if we have a lever and we have a fulcrum, there are a couple of ways that we can calculate the efficiency, or actually I should say the IMA. We can look at the differences in the distances. So if this is where you are applying your force, then this would be your dE to the fulcrum. And if our object were a boulder that we're trying to move over here, this would be our dr, this would be our fr, and this would be our fe. So we can use just the length of that part of the lever. We could also use the distances that we have to move, but usually this is an easier way to look at it. This brings us to efficiency. There are two equations that you want to be familiar with. In fact, though, these two equations are the same. So we can think of efficiency as AMA over IMA times 100, or as the work output divided by the work input times 100, where the work output is your FRDR. This is the force and distance of the resistance. And your work input is your FEDE. This is the force and distance of the effort. So they go together. Now, which equation you use is typically based off of what you've calculated before the efficiency. If you calculated the AMA and the IMA beforehand, it's easier to do the ratio of those. If you calculated the work output and the work input before, it'll be easier to use this as an equation. If you didn't do either, whichever one is most convenient to you, it will probably be easiest for you to work with. So, let's do a quick calculation, a quick practice. A sledgehammer is used to drive a wedge into a log to split it. When the wedge is driven 0.20 meters into the log is separated a distance of 5.0 centimeters. A force of 17,000 newtons is needed to split the log, and the sledgehammer exerts a force of 11,000 newtons. What is the IMA? And so for this, we need to think back to the equation. IMA is a ratio of the distances, the dE over dr. And so in this case, if we're looking for the IMA, we're looking for the distances. And so we look at this. Back to the problem. We are told that the wedge is driven 0.20 meters into the log. That is going to be our dE. The log is separated a distance of 5.0 centimeters. That's going to be our dr. Now, before we can do this calculation, we need to make sure that our units are matching. It honestly doesn't matter which set of units you choose. It's always easiest to be consistent and to move it into the base unit, though. And so in this case, if we have 5 centimeters, that's going to be equal to 0.05 meters. And so for this equation, all we have to do is 0.20 divided by 0.05, and that gives us a 4x advantage for the ideal mechanical advantage. What you'll notice here is that we don't have any units because the units up here and down here are both meters, and they get crossed out when they are divided. And so in this case, the way we show that it doesn't have any units is by just using the x. So this is the ideal mechanical advantage. It's going to be 4 times. So what is the AMA? The AMA is the ratio of the forces. It's going to be the FR over FE. So we look here. A force of 17,000 newtons is needed to split the log. That's the output. That's what the system is trying to do. And the sledgehammer exerts a force of 11,000 newtons. That is what the force that is input into the system. So that is our FE. And so when we calculate this, we can do 17,000 divided by 11,000. And that gives us 1.5x. So the actual mechanical advantage here is 1.5 times. And so that's what a wedge does in this particular case. Now, if we're looking for the efficiency, if we've already calculated the IMA and the AMA, if we go back here, this equation is going to be the easier version. Rather than having to recalculate the work, we can go and use the values that were given for our AMA and IMA into our calculation from there. So in this case, we have our efficiency is equal to the actual mechanical advantage divided by the ideal mechanical advantage times 100. And so when we start plugging this in, our AMA is 1.5 divided by 4 times 100. And this should give you 38%. And that's it. We're done. What I want you to do for practice are these two problems. You can go and pause the video, try to work these out, compare your answers with those around you when we get to class.